Notation and mathematical representation. Welcome, everyone. Before we dive into the mechanics of sequences, let's take a moment to look at our first slide, titled Notation and Mathematical Representation. Now, you might wonder why we spend time talking about symbols before we even start calculating. Well, in mathematics, standardization is absolutely essential. Think of it like a universal language. Without shared rules, math would be chaotic. Specifically, when we begin discussing arithmetic progressions, or AP for short, using a consistent set of symbols is what allows us to communicate complex ideas clearly and without any ambiguity. We want to make sure that when you see a symbol, you know exactly what it represents, no matter who wrote the problem. In this subsection, we are going to focus on two main things. First, the specific notations we use to identify individual terms within a sequence, and second, the mathematical relationship that defines what we call the common difference. By the end of this lesson, you'll be able to read these mathematical statements as easily as a sentence in a book. Understanding the notation of terms. Think of a sequence simply as an ordered list of numbers. To avoid confusion, we don't just point at a number. We use a specific label to refer to a number based on its position in that list. We typically use a lowercase letter, a, with a small subscript number attached to it. That subscript is the key. It tells us exactly which position we are talking about. For instance, the very first number in our sequence is called the first term, and we denote it as a sub-1. You might notice in some of your textbooks that they simply write this as a without the subscript, but a sub-1 is much more precise. Moving down the list, the second number in the sequence is denoted as a sub-2, and the third number is a sub-3. But what happens if the sequence is incredibly long or even goes on forever? We can't possibly list every single subscript. This is where we use a sub-n. Here, the letter n represents the position number. So, if we want to talk about the 10th number in the list, we simply say a sub-10. This, a sub-n, is what we call the general term, and it allows us to discuss any position in the sequence using a single, universal formula. Keep this notation in mind, because in the next slide, we will use these exact labels to define the mathematical relationship that makes a sequence an arithmetic progression. Now that we understand why standardization is so important for clear communication, let's dive into the actual notation we use to identify numbers within a sequence. The mathematical relationship of the common difference. Now that we understand how to label each number in our list using subscripts, let's look at the actual rule that makes a sequence an arithmetic progression. An arithmetic progression, or AP, is formed by adding a fixed value to the previous term. We call this fixed value the common difference, which we represent with the letter D. While we often think about this as adding a value to move forward, we can also represent this exact same relationship using subtraction. If you take any term in the sequence and subtract the term that immediately precedes it, the result will always be that same common difference. To see this in action, let's look at the math. If we take the second term, a sub-2, and subtract the first term, a sub-1, it equals D similarly. If we take the third term, a sub-3, and subtract the second term, a sub-2, it also equals D, and if we take the fourth term, a sub-4, and subtract the third term, a sub-3, we get D once again. To make things much more efficient, instead of writing out every single subtraction, we can represent this as a single, continuous mathematical statement for any AP. We write this as a sub-2 minus a sub-1 equals a sub-3 minus a sub-2, and so on, all the way to a sub-n minus a sub-n minus 1, which all equal D. This equation is the heart of the topic. It tells us that the gap between any two consecutive terms remains constant throughout the entire progression. This consistency is exactly what we will use to solve the real-world problem coming up in the next slide. Real-world application example. Now that we have understood the theoretical notation and the formula for the common difference, let's see how this actually works in a real-life situation. Imagine a student decides to start saving money in a piggy bank. On the very first day, they deposit $50. From the second day onwards, they make a point to add exactly $10 more than whatever they added the previous day. Let's break this down into a step-by-step mathematical representation so we can see the pattern clearly. In step 1, we need to identify our terms. Using the notation we learned in the previous slide, the first term, which we call a sub 1, is 50. On day 2, we take that 50 and add 10, so our second term, or a sub 2, becomes 60. Following that same pattern, for day 3, we add another 10 to 60, giving us a third term, a sub 3 of 70. By day 4, we add 10 again, making our fourth term, a sub 480. Now, in step 2, we are going to apply the mathematical relationship we discussed in the last slide to verify that this is indeed an arithmetic progression. We will use the formula where a sub 2 minus a sub 1 equals a sub 3 minus a sub 2 equals a sub 4 minus a sub 3, all equal to d. Let's do the math. 60 minus 50 gives us 10. 70 minus 60 also gives us 10. And 80 minus 70 results in 10. Finally, in step 3, we reach our conclusion. Because the difference between each consecutive day is constant, we can officially state that our common difference, d, is 10. So our sequence is 50, 60, 70, 80, and so on, where the first term, a sub 1, is 50 and the common difference, d, is 10. As we move to the next slide, I want you to pay close attention, because I'll show you some common pitfalls where students often trip up when performing these exact types of calculations. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of an arithmetic progression, it is very easy to make small errors that can lead to incorrect answers. First, let's look at the incorrect subtraction order. This is a very common mistake I see students make. When we are looking for the common difference, you must subtract the earlier term from the later term. Some students accidentally subtract the succeeding term from the preceding term, writing a sub 1 minus a sub 2 equals d. This is incorrect. The correct way to represent this is a sub 2 minus a sub 1 equals d. Why is this distinction so important? Well, as we saw in our previous example with the piggy bank, if the sequence is increasing, your common difference should be a positive number. If you subtract in the wrong order, you will end up with a negative common difference, which completely changes the nature of your progression. The second mistake to watch for is confusing the term with the position. It is easy to get lost in the notation, but remember, n and a sub n are not the same thing. Think of n as the position, for example, the fifth place in line. On the other hand, a sub n is the actual value or the number sitting in that position, such as the number 25. Keeping this distinction clear is vital for the formulas we will be using in our next lesson. Key takeaways. All right, we have reached the end of this lesson, so let's take a moment to recap the essential points we've covered today to ensure you have a solid foundation for our next topic. First, remember that a lowercase a with a subscript 1 represents the first term of our arithmetic progression. This is your starting point. Second, we use a lowercase a with a subscript n to represent the nth term, which we also call the general term. This is a very powerful tool because it allows us to talk about any position in the sequence without having to list every single number. Third, we have the letter d, which stands for the common difference. This is the constant value that we add to each term to move to the next. Now, the most important mathematical relationship to memorize is this. A subscript 2 minus a subscript 1 equals a subscript 3 minus a subscript 2, and so on, all the way down to a subscript n minus a subscript n minus 1, which all ultimately equal d. This string of equalities is what proves the gap between our numbers remains constant. Finally, a quick reminder to avoid the mistake we discussed earlier. When you are calculating the common difference, always subtract the previous term from the current term. If you flip them, you'll end up with the wrong sign, which can lead to errors in much more complex problems later on. Keep these notations in mind, and you'll be well prepared for our next session, where we will start using these to find specific values in much larger sequences.